All right, so I want to go over molecular shapes with you a bit. So remember that molecular shapes are based on the Vesper model, and the VS stands for valence shell. And the EPR stands for so we have valence electrons in the s and p orbitals, right? And those since they're all negative charges, they'll repel each other to occupy as much space in a three-dimensional plane as possible, and that gives us shapes. So it's based widely on hybridization, right? So there are 5 basic shapes, right? So we have linear, right? So if you look at our hybridization, we always start with, so wherever you see a line, so a line, remember, signifies 2 electrons, so a possibility of 2 electrons that can occupy an orbital. So if you look at here, we only have S. Now, this is an exception. The only time we see this is in H2, right? Because there's only a possible a hybrid, an S orbital, right? So if we look at here, so if we have 2 directions, S, then we start counting, so SP, right? So this is SP hybridization. Let me make my lines a little finer. Right, so both of these right here are linear, right? So they're both linear in nature, okay? And it could be linear triatomic, right? So there could be 2 more atoms on the side, right? If we look at here, the next one, we start with S, and we start counting P's going in directions. So if there are 3 directions off the center atom, right, then we have sp2 because there are 2 p hybrid orbitals, right? So this is going to be trigonal planar. It's going to be a flat molecule, and it's always going to have a hybridization of sp2. Right. So the next 3, so I have S, I have a P, I have an S, because unshared pairs, remember, occupy an orbital. Same thing here. I have S, I have a P. So all 3 of these are sp3. And that applies to all of them. Right? So all 3 of those are sp3. But remember, shapes are named off of things that are bonded and not after orbit hybridization. So this one right here is going to be tetrahedral. Right? So what they talked about in the one video is if I have 4 atoms, right? So if I make my other atoms this color, if I have 4 atoms, it could be trigonal planar. If you look at this tetrahedral, if I have 5 atoms, tetrahedral, this next one is pyramidal. If you look at pyramidal, oops, I have 4 atoms in pyramidal. So there's 2 ways to look at it. If I have 4 atoms and I have 1 lone pair, it's pyramidal. Or you could say that if I have 4 atoms and it's sp3, it's pyramidal. So either one works. This one down here right, is going to be bent. Right, so I've got linear, those are my 5, right? And I have 3 atoms and 2 unshared pairs, or what they call lone pairs. Right, 2 lone pairs. Right, and remember that it's also sp3. So as we go to look at that, we'll start to look. So the important thing for the test coming up is make sure you know, I'll give you some basic molecules. You need to know the stock name, the generic name, as well as the regular name, as well as the chemical name. So methane is CH4, right? So if we look at here, just a little review for you. You have your molecular formula, your structural formula, your ball and stick, your spatial, and then this is another representative of your ball and stick. So remember the dashed line is away. Boy. Let me rewrite that. The dashed line is away, and the wedge so it's meant to give you a 3-dimensional picture, right? All right, so things you need to know, right? So if I have my tetrahedral shape, so this shape was tetrahedral, right? My bond angle is 109.5. So each bond here is 109.5 degrees. So that's the same bond there, is here, is here. It's a symmetrical molecule, right? So each of those length is 109.5 degrees. There are 4 single bonds, 1, 2, 3, 4. So there are 4 sigma bonds. So you need to know the sigmas and pi's associated with these molecules, right? My hybridization, right? Right here is sp3, because we already said that, right? So make sure to know that tetrahedral, right, forms kind of that pyramid with something coming off the top. You need to know that tetrahedral is sp3 hybridization. It has 4 sigma bonds. Those are linear bonds between 2 atoms, right? And I show you that over here to the left, right? And that the bond angle is 109.5. So that's that shape. Oops. If we look at the next one, pyramidal, right? So my ball and stick here off to the left, right? Remember that I will have an unshared pair up here, but when we draw our ball and stick, we leave out those unshared pairs. If you can see the Lewis here, it shows the unshared pairs. But remember, since it has those unshared pairs, right, they take up an orbital. So if you see down here, you leave the unshared pairs, these right here are down there, right? So they do take up an orbital, and they push down on the bonds, right? Because of that, my bond angle here is around 107. Now it's 106.7, but we'll just round it to 107. So it's around 107 degrees, right? All right, so my hybridization is sp3. Oh, so remember, you need to know your molecules. Ammonia, NH3, right? So my hybridization is sp3. My bond angle is 107, right? And there are 3 sigma bonds, right? Because there are 3 single bonds. Okay, so you need to know all those 3. And that is my pyramidal shape. If we look at bent, right? Again, my hybridization for bent we talked about is sp3, right? And that's for water or H2O. So it's sp3. My bond angle here is 104.5 degrees. Right, that's my bond angle. Remember, because I have two unshared pairs, they squeeze those bonds down right away from them. Right, it's 104.5 degrees. And since I only have two atoms attached, I have 2 sigma bonds. Right? And you can see that right here as well. Right? So when we talked about earlier, right, the hybrid bonds, right, the hybrid orbitals, have a tetrahedral shape, but the shape of the molecule is based on what's attached. Right? If we look at all 3 of the sp3s, right, if we looked at them all together, this would be CH4, this would be your methane, right? So I have a carbon, and each of these is a hydrogen. And remember, I have 109 degrees. If we look at this is our NH3. Right? Got a hydrogen, hydrogen, hydrogen. There's my N, right? We got 107 degrees for our bond angle. And this is my H2O. Right? So here we have O in the middle. We have a couple of H's here, and we have our unshared pairs, and they're pushing those bonds down, so I get 104. So the more unshared pairs I have, the more it squeezes it toward the bottom. Right. Trigonal planar. So trigonal planar, so boron's at metalloid, right? So boron trifluoride, or BF3. Boron's at metalloid, so it doesn't really follow the octet rules. It only wants to form 3 bonds, right? It only wants to form 3 bonds. Remember my hybridization, we just talked about a little while ago, is sp2, right? Because I have an s orbital and 2 hybrid p orbitals, right? So it's sp2. It's split equally, so my bond angle is 120 degrees. And since this has 3 single things attached, it would have 3 sigma bonds. So boron trifluoride is trigonal planar, means it's flat, because that's the way that I can get each fluorine as far away from each other as possible. Right, so molecular shapes. Linear, carbon dioxide is our example. Right, so carbon dioxide is our example. Then it looks like this. So carbon dioxide, right, will have 180 degrees. Its hybridization, like we said, is sp2, or is sp, because I only have 2 directions off the linear atom. Right? So this one, because it has 2 double bonds, has 2 sigma and 2 pi bonds around each carbon. Right? So if you look at it here, right, each oxygen is actually sp2, right, as far as hybridization, but the molecule is sp, right, at the carbon. So it's sp2 at the oxygens, and it's sp at the carbon. Right, so let me give you some examples. Let me give you some more examples. So if we did H2CO, right, and so we could say that if we looked at a hybridization S, P, P, because it's based on directions around the center atom, so it's sp2, right? If we looked at shape, right? So my bond angles, this is around 120. It'll actually be less than 120 because of the double bonds there, right? But it's around 120. it's got 3 sigma bonds and 1 pi bond, right? And if we look at it, this is 2.5, this is 3.5, and this is 2.1, right? So I am going to get a pull in that direction, so it is polar as well. There's no axis of symmetry, right? So if we look at that, those are the things that you need to know. You need to know how to do it. So if I look at PCl3, right? So I get phosphorus. Right, so I'd get that. So this is 2.1. This is 3.0. Right, so if we look at this, we would get our hybridization. Remember I had an S, P. So it's sp3. We would say that this is pyramidal, right? I didn't talk to you about this one up here. This one up here was planar. Right, so this one is pyramidal. All right, so if we count, we've got 3 sigma bonds. We have 0 pi bonds, because there are no double bonds associated with that, right? And it is polar, because I have a difference greater than 0.4, right? It's going up toward those unshared pairs, right? So I've got polar bonds. Let me give you another example. If I keep on. Let me give you an exception. So every once in a while you get an exception. We can do PCl5. I'm going to draw it without right. This is what's called bipyramidal, because it makes a pyramid on the top and the bottom. Right, so it makes a pyramid on the top and the bottom. So if we looked at our pyramid, we would go like this. Right, so you would have right, so we have a pyramid on the top and bottom. So it's bipyramidal. Right, so but if we looked at hybridization, S, P. So I have sp3, but the problem is I have an extra one. So after I go to sp, my next energy level is D. So this is called sp3d, because I have to start adding D's after my S's and my P's. Right? So this is called, and that will make you this is bipyramidal because it has 2 pyramids, one on the top and one on the bottom. But I won't make you responsible for that shape. But know that it's sp3d, so once you run out of P's, you got to go to your D's. If I did SF6, right, then that would be something like this. These are your exceptions. Oops. That would be S, oops, 6, that's my 6th F. Something like that, right? And that would be S, P, so this would be S, P, 3, D, 2. So you just start counting D's after valences, right? If you look at these, right, so now we get if you look at these, right, they're symmetrical. So this would be non-polar. This one is symmetrical as well, so it would be non-polar as well. All right, so hopefully that helps you with shapes. So remember, I think the big takeaway is know the examples I gave you, know your bond angles, right? But if we came all the way up to here, this is the big key. Make sure you write this on your notes, that the different hybridizations tell you the shapes. The hybridization off the center atom will always tell you the shape. Hope this was helpful, and I will talk to you soon.